Alright, so we have a 3 here, and we'll be solving for the points at A, E, and the rod CD. So the first looking at this, we can see at E, it's a smooth journal bearing. So that means forces connect along the y-axis and with a moment without interference. So that means only in the x and the z direction there's going to be forces. So I'm drawing the force diagram, because that's the first thing we do when we approach these problems. We're going to have AX, AY, AZ. Here's going to be our force along the rod CD. Our forces at E, which is the smooth journal bearing. So EX and EZ. And keep in mind there's no forces in the Y direction because the rod is free to move in that direction. And of course the mass of the hanging weight. So the second thing we do is now we do the sum of the forces and also the sum of the moments. And I already drew this out to save some time, so it takes a while. So here's the sum of the forces. So I just combined all the forces as I drew in the force diagram. So the AX is in the I direction, AY in J, AZ in K, and as you can see, EX is in the I, EZ in the K. And so now we're going to combine or write equations for like terms. So all the terms in the I direction we're going to combine. So it's just the AX and the EX. That's equal to 0. And we do the same thing for the J and also for the K. And this is basically the process you'll be doing for a lot of these kind of equations you might see. If you see this kind of equation or problem on the final, this is basically the process you want to do. So in the J direction, the only force in the J direction is AY. So we already solved, that means we know AY is going to be 0. So that's one of the components for the ball and socket joint at A. Then for K, we just have the AZ, EZ, the force along the rod, and the hanging mass. So let's write that down real quick. Okay, then also, so since we did these things, that means we have 3 equations. But also keep in mind with our force diagram, we have 6 unknowns. So that means since we have 6 unknowns, we want to eventually get to 6 equations in order to solve for the 6 unknowns. So now we'll do the sum of the moments. So keep in mind the moment is equal to the r, which is the distance from the radius, or not the radius, it's the distance from the axis or the origin, whatever the problem, whatever we choose really, cross the forces. So in this problem, we want the moment to be at A because since there's 3 forces at A, you can really simplify the problem a lot. So here I'm drawing the R's we want to. So here's the R for AF, and so we're gonna have to solve for that. And so it's just a distance. So since we're doing the moments at A, that means it's going to be this distance from A to whatever the force is. And so we're going to have an RAC, an RAF, and an RAE we need to find in order to perform the sum of the moments. So for the RAC, looking at this diagram, it's 1 foot in the Y direction and a negative 1 foot in the I direction, or the X. So it's going to be negative I plus J. Then for the RAE, looking at the diagram, it's only 2 feet in the Y direction. So it's only going to be 2J. Then likewise for the RAF, it's going to be 3 feet in the positive Y and 1.5 in the positive X direction. So it's going to be 3I.1.5J. Oops, sorry about that. It's actually a typo. That should be 3J plus 1.5 I. But I'll fix that later. Okay, so I just also did this ahead of time to save some time. And this is just the components for some of the moments. And so remember, it's going to be the distance from the axis, which we said was A, to the force, so RAC to the rod. The next one's going to be the RAE cross the force at E, and then RAF cross with the weight, which is the force. And then here it is when you plug it all in to save some time. And then similar to some of the forces, we want to, well, actually, you want to simplify this down a little bit. So one thing to keep in mind with these is to use the, oh, I forgot this little part. So a cool trick that I use, you can use, if you know the trick, like whatever you do to perform these, go ahead. I use the I to the J to the K method, and then go back to I. So this is kind of a good visual way for me to solve this kind of problem. So for the first one, it's I cross with K. So since that's going in against the arrow's pointing, that means you're gonna do the sign change. So it's gonna be like I to K, then to J. So since it's not following the flow, it's gonna be a negative. You gotta change the sign for it. So 1 times FDC is just gonna be negative, or FDC J, and since it's going against the flow, it's negative. Then for the J cross K, it's going with the flow, so that means there's no sign change, so it's going to be negative FDCI. Then for the next component, it's going to be J cross I. It's going against the flow, so it's going to be negative 2 times EXK. Next is going to be J cross K, and since that's going with the arrows, it's going to be there's going to be no sign change, so just 2 times EZ. Then the last part, it's going to be I cross K, which is again going against the arrows, the opposite direction. So that means there's going to be sign change. So 1.5 times 250 is negative 375, but since it's going against that direction, it's going to be positive. Last, J cross K is going with the right direction. There's no sign change, so 3 times 250 is 750, and this would be I. So it's just like when we did the sum of the forces. We want to combine the components in the I, J, and K. So first for the I, we have F, DC, and 2 EZ, and negative 750. So write this equation out real quick. Alright. Then for J, it's going to be, oh, forgot the equal sign. And for J, we're going to have the negative FDC 375. So just those two. And we actually can solve for this just because there's only one unknown for this equation, but we'll save it for later. Then for K, there's only one component for K, which is just the negative 2EX. So let's write that down real quick. And that's going to be equal to 0. And then we can solve for that. It's going to be EX is equal to 0. And we can do the same thing for the force DC, which will equal 375 but let's do that towards the end. So now at this point, we have three previous equations. Here's our equation 4, 5, and 6. So since we now have 6 equations, and let's see, 6 unknowns, we can therefore solve the problem now using a system of equations. So you can use reducible echelon form, some kind of program, like Wolfram-Ralph, if you have a T89, whatever you choose. And so doing that, this is going to be the answers for it. So at the end, you will receive these components, A, E, and the force along the rod, DC. So there you go. That is the solution to the problem. So usually when you approach these kind of problems, so 3D equilibrium using the vector analysis, you first want to write out your force diagram. And this is important to kind of visualize the forces and to make sure you keep account of everything. Second, you want to solve for the sum of the forces, and that way you can get some equations. So the main goal is just to find how many unknowns you have, and then to receive just as many as equations so we can solve for it at the end. And so the sum of the forces will give us our first set of equations. Then for our sum of the moments will give us the other set of equations. And usually you want to plan to choose the position or point that kind of has the most points there. So for this problem we did A because there's 3 forces there, so we can simplify the problem a lot more. And then with this, keep in mind M is equal to the R cross F, so F is the force, and R is the distance from the point we've chosen to the force. And then lastly, when we have all the equations we need, then we just solve for the system of equations. Okay. And a couple of things you want to keep in mind with these problems is, for these problems, as you can see in this example, it's purely math. So it's just basically just finding the different components and then just performing the math for it. And then also another thing to keep in mind is that the force and the moment are both vectors, which we saw with I, J, and K components. And so that's just one thing that allows you to solve like a complex problem just by using the components or the vectors of it in order to solve for these problems. So hope this review was helpful. Best of luck for the final, and yeah, good luck. Alright, well, thank you for watching my review.